Hello, Sauce here. This is a lesson on the derivative. What I have here is a function f of x is equal to x squared plus 4. We've seen this expression in the past, but we called it the p function for position as a function of t time. And in that lesson, we were thinking of the context of the position of an object. So when we calculated the instantaneous rate of change for that position function, we found the function for the velocity at any given time t. Here we have an abstract function, but we can calculate the instantaneous rate of change just like we did before, and if we were to do that, we would get the IROC of f of x is equal to 2x. And again, that calculation was done in a previous lesson. But in general, the IROC, or instantaneous rate of change of any function, is given by the expression that ought to be familiar by now, the limit as h goes to 0 of f of x plus h minus f of x all over h. And we can see that because we're using general terms here, f for the function name, x for the variable, there's no context here, but there's still the meaning of the instantaneous rate of change. Calculus is really big on this idea. And when we're in calculus, we don't often refer to this expression as the instantaneous rate of change or the way to calculate it. Calculus has a word for the instantaneous rate of change called the derivative. So to say or ask the derivative of f of x is the same thing as the instantaneous rate of change of f of x. And there is notation for the derivative rather than spell it out and use this word. If we wanted to find the derivative of f of x or symbolize it, then we use this notation. We put a prime symbol or a little tick mark to show this, the derivative of f of x. Or we could say f prime of x. So if this, f prime of x, means the derivative, and the derivative is the same thing as the instantaneous rate of change, and the instantaneous rate of change can be found by using this expression, then the derivative of f, given this notation, is the same thing as this expression, the limit as h goes to 0, of f of x plus h minus f of x all over h. And this is a really big deal. This is the backbone of calculus. It uses the limit, which is introduced in calculus, but it's using the limit here to find what we call the derivative, the instantaneous rate of change. And when we spell it out with this notation, this is called the definition of the derivative. Let's use it. Again, this is nothing new. We have been finding the instantaneous rate of change of functions for many previous lessons. In this case, we're going to define a function g of x is equal to the square root of x. And now that we understand this notation or have been introduced to it, then we can be very direct, and the question could be, or the instruction could be, find g prime of x. In other words, find the derivative of g. Or in other words, find the instantaneous rate of change of g of x. So this becomes the derivative of g is equal to the limit as h goes to 0 of g of x plus h getting a little sloppy here, minus g of x all over h. And now let's apply the specific function. This will be the limit as h approaches 0 of the square root function, which we're calling g, composed with x plus h, minus the square root function g that we call g, square root of x all over h. And again, we have a division by 0 error if we were to take the limit right away. And we know from previous practice that we ought to expect to manipulate this algebraically in order to eliminate the division by h so that we can take the limit. What algebra is going to help us with that? This is a little sophisticated. We are going to manipulate this, but how? We're going to take advantage of what's called the difference of squares factoring pattern, which on the side I'm going to remind you of. A squared minus b squared is equal to the factored form a plus b times a minus b. How's that going to help us? Well, if we consider this numerator, which is the difference between two radicals, and we're to consider that that piece is one factor in this pattern, then what I need to multiply by is the other factor, which will turn it into the difference of squares, and the square of a radical will eliminate the radical. It's a lot to keep track of. Let's see it in action. If I'm going to consider the numerator that exists here as one part of this factoring pattern, then I need to multiply by the other factor, which is x plus h plus, or the radical of x plus h plus radical of x. And I can't multiply by something like that because it would change the value of my expression. But I can multiply something like that if it's a version of 1 as something over itself. So if I include an x plus h, radical x plus h plus radical x, and I multiply by the fraction composed, numerator and denominator of the same thing, then it's a multiplying by a version of 1, and we can do that because multiplying by 1 doesn't change the expression, or doesn't change the value of the expression. But I would choose to do this because now the numerators in both these fractions are the factors on this side of this factoring pattern, which means that in my next line of work, I can take these two factors and show them as the difference of the square of the first term minus the square of the second term. And the square of the first term is quite simply x plus h, because the square eliminates the radical. And then I'll subtract the square of the second term. And the square of radical x is just x. I still have to multiply h by this denominator, so I get h radical x plus h times radical x. Notice that I put the denominator that I was multiplying h by in parentheses so that I need to distribute the h, and I'm still taking the limit as h goes to 0. But look what's happened. In the numerator, I have positive x term and a negative x term that cancel out. In the denominator, I have an h factor that will cancel out with the only remaining term in the numerator. So this h will cancel out with this one. It turns the numerator into 1. And what's left in the denominator is radical x plus h plus radical x. We're still taking the limit. At this point in the process, I no longer have a division by h by itself. So if h goes to 0 now, it will not cause a division by 0 error. I can attempt to take the limit. Let's see what happens when I do. 1 in the numerator. This radical becomes radical x plus 0 plus radical x. I've taken the limit. That's why you see I do not show the limit statement out front, because it's been applied. I can clean up this denominator here. I still have a 1, but I have a radical x plus a radical x, so it's best to show that as a 2 radical x. This expression can't be further simplified. But what have I arrived at? Remember my original project. I was trying to find the instantaneous rate of change of g. Now we're calling it the derivative of g. And there it is. This is a function called the derivative of g, which will calculate the instantaneous rate of change of the function that it came from. If this was a position function, if g was a position function, then this derivative would be the velocity function.